Welcome to a lesson with Dr. Powell. Let's take a look at why, if we have a functor between two abelian categories that preserves direct products and sums, then F is additive. That means it's a homomorphism between Hom sets. The addition of two functions before we apply the functor translates to the addition of the images of those two functions via the functor. Okay, so if we're going to do this and use the fact that the functor preserves direct products and sums, and we want to look at sums of functions, it would be nice if we could represent a sum of two functions in terms of direct products and sums. Okay, so let's take a look at that. Here's a little description. Let's look at A plus A, which is actually isomorphic to A cross A. Now, this sum, A plus A, is a colimit, and it has something called a cocone. All right, so there's a simple diagram, just two copies of A, and there's inclusion maps into it. Those inclusion maps make up what we call the cocone for this colimit. Likewise, there's projection maps, which you could think of coming from the direct product, A cross A, which is it's isomorphic to, and that would be part of the cone of A cross A thought of as a limit. So our functor is actually going to preserve that cocone and cone. So actually the projections, the images of the projections will be projections when we move along to the to what the functor f will do. But before we get there, let's look here for just a moment. The inclusion maps, projection maps, if we were to think about these projection maps, they come actually from the universal property of the direct sum if we're given the inclusion maps. If we're given the projection maps, then the inclusion maps come from the universal property of the direct product. And I have a couple diagrams here to illustrate that. Now, how do we express the sum of two functions here? I have it written here. Let's look at that for a minute. I have this map H. This map H is the unique map that makes this side of, right here, so from H of I1 equaling F and H of I2 equaling G. All right, so it's the unique guy that does that. So, but now here I said that H was equal to this by uniqueness, and that is because F of P1 plus G of P2 actually makes this diagram commute. So it must be the unique one, all right? So we have, how does it make it commute? Can we see that? Well, if we just take this and precompose I1 to it, what happens? I1 comes in and comes to P2, and what does P2 do it? Well, it sends it to 0, thinking of how, see, P2, look at this little diagram right here, right? P2 of I1, by definition, is going to be 0. So that zeroes out. And then when I1 comes into here, P1 of I1 is actually going to be the identity, and you're just going to get F on this side as. So it makes this side of the diagram commute. It'll also likewise make this side of the diagram commute. So we know that this map right here is H, and we can think of F plus H as being H composed with this map. What is this guy? This is the sum of the two inclusion maps. I put a little identity here just so we can realize, I mean, these are two different copies of A. If we just want to think of these two copies of A as being the same copy of A, we can pull back via the identity map. I mean, we may as well just kind of merge all of this picture together as just a single A, though, if we wanted to, and just think of I1 plus I2. Okay, so we have that, and remember that if F preserves direct sums and products, that means it preserves the limit cone of the direct product and the limit and the colimit cocone of the direct sum. All right, so let's see what happens. To that diagram, F, it preserves compositions. And so we have another diagram here. And it also preserves the cone and the cocone, which means that f of I1 is actually the inclusion map to this direct sum, and f of I2 is the other inclusion map, and you have the projection maps. Likewise is just the images. That's kind of nice here. As we move along, everything's just, we just take f of everything and we get what we need. F of the identity, it's a functor, it's just the identity map. So we have this diagram, and this unique map, f of h, because we can get, by uniqueness, we get the same type of thing going on for the same reason because of these being inclusion and projection maps. We can express it the same way we did h in the following way. It makes a diagram commute for a similar reason. So that's nice. We know what f of h is that way, and we can write it down that way by uniqueness. We also can think, okay, I'm going to just think of I1 as this right here as just being I1 plus I2. And if I run the functor on the sum f plus g, it splits over the composition, and I get f of h of f of I1 plus I2. Now, a key fact that we're going to use is actually that at least there's going to be an instance of additivity, and that's going to transfer to the one we want, which is right here. The functor applied to I1 plus I2 gives you f of I1 plus f of I2. Now, why is that? There's a couple diagrams here to show you. Well, first of all, if you apply the functor to this diagram, you get f of I1 plus I2, and the direct product was preserved. So this is actually f of I1 plus I2 makes this commute. It is the unique one that makes it commute. It's just the image of that. But also, notice that f of I1 plus f of I2 will also make a commute. Just run it through. Just put it in. So we can try that out here. Let's see. So if we did something like, okay, maybe I'll do it right here. So if we have, for instance, f of P1, and we have f of I1 plus f of I2, notice what happens. F of P1 comes in. When it distributes to this part, you're going to get the 0 map for the same, different projection with the different inclusion. We'll give you 0. And then this one right here will give you actually the identity map. Hey, that's the identity map coming up here. So, because this is the projection, this is the projection of here for this direct sum, and that's the inclusion too. So we are, or direct product rather. So we have, so we end up getting that this commutes. So we do get this. This is by using universal universal property, saying that things commute, that we get this equality. Now we just basically just use that equality, and we're pretty much done. So we have this. We know what f of h is. It's equal to this of this sum right here. And if you put this in and distribute using the ideas of things zeroing out or becoming the identity, we get it. So we know that this functor applied to f plus g is going to be the sum of a capital F of little f plus capital F of g. Thanks for watching.